Yay, picking up with example 1. Did it say before lunch? Yes, it saved. Yeah, the video saved today, so that's good. All right, so just to recap, you could think of this as being particle motion, essentially through the XY plane. We studied particle motion already this year, but we were limited to left and right or up and down. It was straight line motion. Here we finally get to travel through 2 dimensions, not 3 yet. That would be another day. But traveling through 2 dimensions, if we break it down into the component distances and velocities, we could do calculus. All right. Don't write on that, but you can do it on there. So we had this particle, maybe, if you want to think about it, at t equals minus 2. It was at the position 0, negative 1, and then it went to the left, turned the corner, and came back to the right. It was slowing down as it turned the corner and sped up as it went to the right. But the whole time it was moving up vertically at a constant rate of a half unit per value of t. So what we want to do now is see what the graphing calculator can do in terms of this. So get your calculator out and go to mode. Now if you scroll down to this line here, 1, 2, 3, 4, the 5th line down, we've been in function mode all year long. Function mode is like what I just called rectangular mode before class, right off for lunch. It's what we're typically used to doing, the X and Y. But if you click to the right, there's parametric mode. We're going to be studying polar in the next chapter, and we're going to study sequences and series in the last chapter, okay? So we're in parametric right now. So click parametric, hit enter, highlight it. Now, when you go to y equals, look what happens. It changes. It's not just y sub 1, y sub 2. You have a pair of inputs, x sub 1 of t and y sub 1 of t. So it acknowledges t as the parameter. So let's go ahead in x sub 1 and type in our equation from before lunch, which was t squared minus 4. Now, where do we get the t value? Yeah, if you look at x, it's always had other stuff there. X, t, theta, n. Those are your inputs for all your different modes. Function mode is x, parametric mode is t, polar mode is theta, sequential mode is n. So if you click that, you get a t now. So t squared minus 4, and then hit enter, and it'll throw you to the y, the pair. They have to happen in pairs. It's t divided by 2. Now, don't just hit zoom 6. If you go to your window, you're going to have another set of inputs now, which are your parameter inputs. T min, T max. T is the independent variable for both x and y. We went from parameter value of negative 2 to parameter value of 3. Now, T-step is interesting. T-step is, the text is T-step. It's how often do you want your calculator to compute a coordinate xy so that I can plot it before it connects the dots. If you put your T-step at the default, which looks like it's 0.13, it's going to compute a new xy value every 1/1300th of a unit, plot it, and connect the dot. So let's just see what that looks like. Now for the x min, x max, we can actually type this in because we already graphed it by hand. We went all the way to the left to negative 4, so let me go to negative 5. Our x max, we went all the way to 5, so let me go out to like 7. And we'll count by ones. And then for the y min, our low point was negative 1, so let me go like to negative 3. And we went all the way up to 3 halves. Yes, let me just go to like 5 or something. And we'll count by ones. So now when I hit graph, you got to watch quickly because it's going to trace it out, not just the path, but it'll trace the right direction. And you might not get an appreciation for the variable speed, but let's see. Ready? 1, 2, 3. Yeah, I went too quickly. But you can actually see what happens. Now notice if you hit the trace button, this is pretty cool. If you hit the trace button, it'll show you on the bottom what rectangular coordinate's at, but it also will do it now with your parameter value intact. If you click to the right on your directional pad, it's going to trace it out for increasing values of t. Look, this is kind of weird. If you click to the right, your graph is actually moving what? To the left. That's kind of weird. But remember, it's tracing it out in terms of t. So here are all these other values that we did not compute. but it computed every 0.1 whatever. So here's what you want to do if you want to see it traced out. Let's do a couple things. Let's go back to the window. If you change your t step to, let's say, 1, look what happens. It's going to trace out faster, but notice, does it look as curvy anymore? No, because now it's computing the exact same numbers we did. Watch, trace. If you click to the right, there's the next one we did. There's the next one we did. We did that one. So that would be our t step. We did it every one. I told you to connect them with a curved line, not a straight line. If you change your t step to 2, that's really going to make the graph awkward looking. It's only computing a value every 2 units, so you're not even going to see the whole graph. So there has to be a happy medium between something that graphs it so quickly, but still gives a lot of accuracy. So let's try this. Let's try slowing down the graph by making it compute more values. So let's try like 0.01. Remember, it was 0.1. If we put it as 0.01, we're forcing the calculator to do more work. It's going to slow it down. Let's try that. Oh, a little bit slower, but not slow enough for me. I like that super slow-mo. So maybe if we go 0.01, put another 0 in there, now graph.
That's how the normal calculator does it.
Yeah.
It's so slow.
This is almost super slow-mo, but you do get an appreciation for the speed when you watch it in slow-mo, right? Oh, yeah. So if you're not using the super deluxe high-speed calculators, maybe it's already slow enough to see. But just keep that in mind. If you want to get an understanding of the speed or the velocity, really, at which it's traced out, just make your t-step a little smaller, and it'll slow it down by making it compute more points. Now if you hit the trace, it's going to take a while to move to the right because we're tracing through a lot of points now, okay? So anyway, there you go. Now, here's another caveat to parametric. We can actually come up with other equations that maybe follow the same path, but that trace out with a different speed, or maybe even a different direction. Maybe there's one that we could trace it out from top to bottom. So let's go now to the bottom down here. What do you notice about the graphs of this one? Okay, let's go back to our calculator then, and let's go to the second available option. Actually, I'm going to have to turn this one off because we're going to have to change the parametric window. So we're not going to be able to compare apples to apples. But if you type in 4t squared minus 4 and t for your y, and you reestablish your parameter to the one I gave you from -1 to 1.5. Notice it looks like we're graphing it now on half the t window that we did prior. You see that? We went from -2 to 3 prior, but now we're only going from -1 to 1.5. So I like halved the parameter value. But what did I do to my equations? What did I do to the y? Instead of t halves, it's now t. So I like doubled it, and this one over here I like quadrupled the t squared. Let's just see what that looks like. If I hit graph again in my new window, ooh, ah. It looks kind of like what? Looks like it's for certain the same path. Did it trace out in the same direction? Yes. Now it's subtle. It'd be nice to be able to graph them side by side, but I don't know a way to do that. Like you're at the Spurs timeout and you see like the red versus the blue dot, who wins, to see which one wins. This one actually traces out a little bit faster. It traced out twice as fast as the other one. So there are several different parametric equations that'll generate the same path, but they will all differ by speed and possibly direction. Let's look at the next set. The next set looked very, very wacky. I don't know where those came from. Maybe France. But let's just type it in and see what happens. I'll do this one in fuchsia. Yeah, fuchsia. We don't get that every once in a while, or not often enough. I need to make sure I'm in radian mode, so I'm checking that. And now I got to scroll down to fuchsia again. All right, so here we go. 4 parentheses, 2 sine of t, close parentheses. Thank you, and congratulations, by the way, you and your teammates. Squared minus 4, and then y sub 4 will be 2 sine of t. plus 1. Now my window changes. It goes from negative 1.57, which maybe you recognize that as pi somethings. Maybe not. Pi halves. To, negative 2.253. All right, ready? Here we go. Ready to watch? Yeah. Oh, you did? At the same time? On different parametric windows? Oh, you found a good speed. 0.5 or 0.05? Oh, okay. Well, let me go ahead and do 0.51 here. I don't want to delete the 1. Something's wrong here. Okay, so let me do a couple of things here. First of all, let me turn this graph off. I graphed both of them. And notice if you hit enter on just the X equal sign, they both turn off. I'm going to go back to a smaller T step. I think sometimes you run the risk of not creating all the points if you don't have T steps small enough. So I'm going to go back to 0.01. That seemed reasonable. Now, this one, again, looks like it traces out the same path. It did trace out the same direction, but it was a different speed. What do you think is going to happen to the speed if it's in terms of sine and cosine? What does sine and cosine do? They oscillate. So have you ever driven with someone that kind of like drives like this? They hit their foot on the accelerator like back, up and down, up and down. That's what's happening here. It's like throbbing. It's going to like go fast and then slow, and then fast and then slow, and then fast and then slow. Okay? So kind of interesting. By the way, the sun's coming out. Yay. Now I'm going to show you later how we can get equivalent graphs and how we can get equivalent intervals of the parametric intervals. Because look what happens here. If I were to graph this function, but I were to use the original parametric window from negative 2 to 3, look what happens. Do I get the same path? I don't. It looks like it is the same path to begin with, but it goes out a little bit further. So if you have a different set of parametric equations and you want to capture the exact same path, you're going to have to restrict your parameter values in a certain way. Now, did you see how it sketched it? Did y'all see that? It didn't just start here on the bottom and move to the left. It actually sketched out a little piece, left it blank, and then came back and jumped and sketched it. So kind of interesting. So the only way to get an equivalent path, which would be your rectangular form, is to adjust your T windows, which is why I had different T windows for each of these three. Okay? So let's summarize now. With rectangular equations, that is, like we've been doing, X and Y's, on restricted intervals. What the heck does that mean? Well, let's look at that real quickly. This graph looks like it could be a sideways opening parabola, yeah? Now, a sideways opening parabola would go on to infinity on both of the branches. At the top, you would draw an arrow, and you'd extend it past the y-intercept on the bottom and draw an arrow. So if you take a rectangular equation and you restrict it to part of it, then you'll have a parametric path. So what we can say then is rectangular equations on restricted intervals show the what? They show the path. Okay, the graph itself shows the path that an object takes. Parametric equations, on the other hand, show the what? They show the speed at which it's being traced out, comma, the what else? Direction. And of course, they still show the what? They still show the path. So you get two more pieces of information by introducing one extra variable. Okay? The only thing is if you were just looking at the graph without seeing it traced out, you're back to the rectangular version. You're like, oh, I don't know which way it was traced out, and I don't know how fast it was traced out. But when you associate those points with the time value, again, by tracing, when you throw that extra piece of information in at each time, you can now figure those other two things out, which is really nice. Okay, now the last thing we need to do here is to eliminate the parameter before I jump too far ahead. Eliminating the parameter essentially means get rid of the t's from the two equations, t is the parameter, and write it as a singular equation in our old-fashioned rectangular form. That is, write it as y as a function of x. Okay? If I do that, we should end up with the equation of a parabola that opens sideways, which means that the y should be squared instead of the x. So any ideas how we can go about eliminating the parameter and writing a single equation in terms of y and x? Think algebra 2. Well, there you go. Take one of the two equations and solve for t, and do what were you going to say? Plug it in or substitute it into the other. Which one's easier to solve for t? The one on the right. Good. So if y equals t halves, t would equal 2y. So I'm going to plug that in right over here for t, and I get x equals the quantity, 2y squared minus 4. And so we end up with x equals 4y squared minus 4. And there is the rectangular equation. That's not a function of x, but if you were to solve it for y, you would have the plus or minus. And the plus would be the top part. It would be a radical equation. And the minus would reflect it across the x-axis. Okay? But again, that would require two equations, and they would go out into infinity towards the right. Whereas the parametrics limit it. Okay? So that's how you eliminate the parameter for a problem like this. You have two equations, solve for one, plug into the other. All right, moving quickly here, let's jump to number 2. We have another set of parametric equations. X equals something as a function of t, and y equals something as a function of t. But notice, there's no parameter values there. So if there's no parameter values there, then we have to assume t is going to be used over the joint domain. And Tori, this is kind of like what you were talking about before lunch. You're not going to be asked to integrate through a value of t where one of them is undefined. So let's figure out the domain of each. Can divide by 0 and can't take the square root of a negative. So on this one here, we know that t has to be greater than negative 1 to make the radical or the radicand positive. And if it's equal to negative 1, then I get the square root of 0, which is not allowed. So my domain of this is strictly t is greater than negative 1. This one over here says t can't be negative 1. So we have to choose a domain that satisfies both, which is, of course, t has to be greater than negative 1. So let's go ahead, and we could do this by hand, but I think you kind of get the idea of how to plug in points. Let's just go to the calculator. Y equals, let me flush the commode here and get rid of all these. The calculator commode. Yeah. Flush. All right. Come back here to unicorn blue, and we type in the first one, and I'll use the horizontal bar, 1 over the square root of t plus 1. There's the first parametric, and then the second one, t over t plus 1. So now we will go to our window, and since t has to be greater than negative 1, we can start where? Yeah, let's start at negative 1. And of course, if it tries to sketch that, it's going to be undefined. And how far do you want to go? You want to try 3? Try 4? Try 5? Let's try 5. And then 0.01, I think that's reasonable. So the first point it's going to calculate after negative 1 would be negative 0.99. All right, let's hit graph. Actually, let's hit graph. We'll adjust the window. Come on. Come on. Keep going. Did you see what happened? First of all, the window happened to be nice, X and Y. It came in pretty quickly from the bottom, like it was excited to make its way towards the Y-axis. And then as I got closer to the Y-axis, it was like, I don't think so. It started slowing down. And it looks like it never even made it, huh? Let's do a couple of things. Let's adjust our window. I don't need to see so far to the left to negative 5. Let's call it negative 1, because it looks like it came in from the right-hand side. let's look a little bit lower than -3. Let's try like -10. Now let's graph it again. Come on! Oh, why are you slowing down? Come on. Stopped. So, does it actually stop right there? Maybe, maybe not. I don't think so either. Here's what I know. I know that the only t-value that doesn't work is -1. Let's see what happens. What would be the first t-value to the right of -1? No. Yeah, it'd be -0.99. You thought Anna-Gata-Davida was long. That's a long song with 9s. It goes on forever. There is no first number, right? Anna-Gata-Davida was like 15 minutes. Okay. So anyway, let's do this. Let's see what the x and y are approaching as t approaches -1. All right, so what would my x values be approaching as t approaches -1? Infinity? It has to be infinity, right? Because what do you get by direct substitution? Indeterminate form? No, you get 1 over 0. Remember, non-zero over 0 is some type of infinity. In this case, it is negative infinity. No, it's infinity. Sorry, it's infinity. You can't be negative on the right side. My bad. And then y. Let's see what the y's are doing. As t approaches -1, what are the y's doing? Well, let's put the y equation there. Yeah, this is -1 over 0. Yeah, this is kind of funky. That's also infinity. That's kind of weird. But is it negative infinity? It is negative infinity. Oops, not -1. So, oh my gosh, how can that be? Let's look at the graph. Let's hit trace. Let's hit trace. Notice when t is -1, it's undefined. When I hit immediately to the right, where are my y values? They're at 10 and -99. So this guy comes in from the bottom. When I take the limit as t approaches -1, I'm actually getting a little bit closer to my starting position, which is not. This thing graphs from right to left.
So it came back down?
So it's coming from the bottom, where x would be coming from positive infinity, and y would be coming from where? Negative infinity. Okay? What you have to start thinking of is we're doing it in terms of increasing t, not increasing x. We don't read this graph from left to right. So as t approaches -1, this graph is coming in from, we just found it. X is negative infinity, so that's way over here on the right, and y was negative infinity, that's all the way down. So this thing is coming from way down here in the bottom right-hand corner coming up. And as I scroll to the right, letting my t value get bigger and bigger and bigger. Now let's come back to here. If we said that our t values had to be greater than -1, how much bigger than -1 can they get? Infinitely large, yeah. So let's do this. Let's now figure out the limit as t approaches infinity of both of them. The trick here is you can't see the t values on the rectangular graph, but we are so used to thinking x is left to right, okay? So this graph is coming from the right, from the right and from the bottom. It's coming from the bottom right-hand corner, and it's moving up and towards the left, approaching infinitely many values of t. Now, why did mine quit graphing? Because I stopped it where? At 5. How close is 5 to infinity? Not very close. Let's compute it first since I have it written down. What would be the limit as t goes to infinity of the x values? That is the first one I wrote here. What's happening to the denominator as t gets really big? It's getting really, really big, and the fraction is getting really, really small, approaching 0. And what's happening to the y values? Leading coefficient over leading coefficient, because it's a polynomial over polynomial, it's approaching 1. So as this thing comes in from the bottom right-hand corner, it's approaching the ordered pair x equals 0, y equals 1. That's supposed to be infinity. Good catch. Yeah, thank you. Yeah, that doesn't make any sense. Now it does. That's why I didn't answer right away. Yeah, I apologize. It's Friday. That's not the first mistake I've made today. So anyway, what's happening, this graph is coming in towards the point 0, 1. And it's coming in like this, very fast, and then slower and slower and slow. Oh, gosh, long hold. Will it ever reach 0, 1? No, but it's approaching it. So if you wanted to sketch it, you could do it like that. Now, here's another thing that I didn't mention on the first one. When you're sketching a parametric graph, it's nice to be able to discern as many of the three things that it gives us from the graph. We certainly get the path. It's going to be hard to graph the speed, right? Yeah, because that's almost like an animated thing. But we can show the direction, right? Arrows. Simply putting a couple of arrows on the line that point in the direction is sufficient, okay? So that shows the direction that it's tracing out. Now let's see if the calculator can handle. Let's change 5 to something that's closer to infinity, like 55. It's closer. Let's see what happens. Graph, come on! Get there, get there, get there, get there, get there. You can almost see the contradiction now, right? Because we've always said, how close can an object get to an object without ever getting there? Infinitely close. Well, now in parametrics, if we're watching an animation of the video, and we can let t time go on forever and ever, and as time goes on forever and ever, this graph is only expected to get closer and closer to the point 0, 1 without ever getting there, you can now feel the frustration. In order to use infinity amount of time to approach a finite y value, the only way to do that is to what? Slow way the heck down. That's good. So the velocity, the horizontal velocity is decreasing, or the horizontal speed is decreasing, okay? Yeah. So anyway, there is your idea of parametrics. We'll probably spend a little bit more time on Tuesday when I get back, doing 1 or 2 more examples, and then we're going to BOTC. We're going to bust out the calculus. Because I know you want to, right? We're talking about speeds and how fast things are moving. And that's the calculus part.